So case 2, that the M1 equals M2, and from the solution of the auxiliary equation, m equals plus minus square root of negative lambda, right? That means if we look for the case that m1 equals m2, that give us negative lambda must be 0. Or we said lambda equals 0. If the lambda equals 0, the m gonna be 0, 0. Only the case that you have repeated solution. If m is 0 and 0, so then the solution of the auxiliary equation, or solution, the general solution will be in the form, so I'm going to write here, the general solution is y equals c1 e to the 0x, right? 0x plus c2 e to the 0x as well. But since we have the repeated solution, what we have to do, we have to multiply by x, or the independent variable, to make it linearly independent. Therefore, the general solution will be in the form of y equals c1 plus c2 times x. Okay, that's the general solution for case 2, the case that the lambda is 0. If the lambda is 0, basically the equation becomes that y double prime equals 0. That's the simple form of the second derivative, that we can find the answer like in, like, we don't need to use any advanced technique to solve for it. But just the case that we look at the case that the lambda equals 0. So the answer will be in the form of y equals c1 plus c2 times x. And now use the condition again, y at 0 equals 0, y at pi over 4 equals 0. For x equals 0, y gonna be 0 equals c1 plus c2 times x, which is c2 times 0. So it already gives us like c1 equals 0. This one gone. Now it just come down to c2 times x. How about when x equals pi over 4? X equals pi over 4, y is still 0. So 0 equals, it looks like everywhere, right? So c gonna be c1 plus c2 times 0. It's true because c1 is gone, and c2 times 0 is going to be 0. So then c2 could be anything. C2 is an arbitrary constant. So that means you can use any value c2, any number c2 to satisfy this is pi over 4. I'm wrong, sorry. Let me clean up this real quick, because x is pi over 4 for the second condition. Just a second. Okay, so this c1 plus c2 times pi over 4, and c1 is already 0. So that means you get c2 multiplied by pi over 4. We know pi over 4 is not 0. That forces c2 to be 0 again. And this case makes c1 equals c2 equals 0. And what does it mean? You get another trivial solution. Okay, so we're going to make a note over here. For lambda equals 0, the solution is trivial again. For case 3, we look for the M1 and 2 in the conjugate complex form. Okay, in the form of the alpha plus minus beta I. And for our case here, we have M equals plus minus square root of negative lambda. To get the conjugate complex, the alpha is already 0. So that means we're gonna have to look for the case that the lambda positive to make it conjugate the complex solution. Okay, so this one, the lambda gonna be positive, because negative lambda is negative number, square root, it gives you the imaginary number. Introduce the variable, the parameter, like omega square again. So omega square, just for our convenience, when you take the square root, otherwise you're going to have square root everywhere when you work on a problem. So omega square see negative lambda. So then the m equals plus minus square root of omega square, or actually the lambda is, let me see, the not negative sign, I'm sorry. So since the lambda is already positive, so the omega square gonna be the lambda. So then we have the m equals square root of negative omega squared. Let me clean this up a little bit. So square root of negative omega squared. And that will give us plus minus omega, and with the I, or the complex number, comes out. We have to remain negative sign in there, right? So from m equals plus minus omega I. So the general solution is y equals no real part, so no e part of the solution. Gonna be C1 times cosine omega x plus C2 times sine of omega x as a solution, as a general solution. Okay. Box this out. Now, use the condition again. Y at 0 equals 0. Y at pi over 4 equals 0. For x equals 0, y 0 equals C1 times cosine 0. Cosine 0 is 1, so we get C1 0. All cases that the C1 is 0. Just for this set of the boundary conditions. And next, for x equals pi over 4, we get 0 for the y equals C1 is already 0, so the cosine term here is gone. And then the C2 multiplied by sine of 0 times omega. No, not 0 again. So x is pi over 4. I'm wrong. So going to be C2 sine of omega times pi over 4. Okay, because again, this is the boundary conditions, the condition from the two endpoints, the left end and the right end. So for this case, the omega is the parameter that could be any real number as long as the omega square equals lambda, which is positive number. Okay, we know that omega is positive. So it depends on the product of the omega and pi over 4 that could make the product of C2 and psi to be 0. So as you recall, the psi function is anywhere between -1 and +1. So we're gonna look for the case for the non-trivial solution. Non-trivial solution. If we make this as a non-trivial solution, since the C1 already 0, non-trivial solution will be in the form of y equals C2 times psi of omega x. So this is our kind of observation that what we're going to get later. But now we're going to find out what would be the option of the lambda that would give us this non-trivial solution. Non-trivial means not 0. So we're going to make the case that if C2 is not 0, if C2 not equal to 0, then the psi omega pi over 4 must be 0 to satisfy this boundary condition. Okay, that means we're gonna find out what is the omega that makes the psi of this omega pi over 4 to be 0. Look at the unit circle. Psi of what angle that give us the value 0? Gonna be the angle like omega pi over 4 equals the n pi, like psi 0, psi pi, psi 2 pi, and so forth, or the multiple of the pi. Okay, multiple of the pi. So we can use this at, again, since omega is positive number, so this is greater than 0, and this number also greater than 0. We're gonna start from the option that's greater than 0. So gonna be omega pi over 4, not including the 0 angle. Gonna be starting from pi and let me see, 2 pi, 3 pi, and so forth. Okay, so we can rewrite this as omega pi over 4 equals n pi as a general solution, and make it n as starting from 1, 2, 3, 4, 5, and so forth. We don't take 0 because the product of omega and pi over 4 always positive. Okay, since omega itself is positive number. This is another sensitive part of the problem. Okay, the index is very important. So then our goal is to find lambda, right? We're gonna use omega to get to the lambda. That means the omega is 4 times n. Okay, 4 times n. As you multiply all by 4 and divide by pi, so you get omega equals 4n. And what is the relationship of the omega and the lambda? Let's go back up a little bit here. So here is the relationship of the omega and the lambda. Okay, omega square is the lambda. So we square this. So then the lambda equals this square. That means the lambda, gonna put the subscript n because it depends on the n value. So lambda n equals 16 n square. For n equals 1, 2, 3, 4, and so forth. Recall the equation is y double prime plus lambda y equals 0. So this is our differential equation. So that means if you pick one n, you get one equation. So like n equals 1, you get y double prime plus the first lambda, which is the lambda 1. Okay, lambda 1, y equals 0. So for n equals 1, for example, lambda 1 is 16, lambda 2 is 16 times 4, or 2 squared, or 64, and so forth. So that means you can have options as y double prime plus 16 times y equals 0 for n equals 1. For n equals 2, going to be y double prime plus 64 y equals 0. If you recall the problems in 5.1, this is just the free and damped problem, right? Free and damped problem that it depends on the K, the spring constant, and also the mass, which is from the Newton's law. So we have options for the lambda that give us the non-trivial solution. That means our lambda n, this one is called eigenvalue, or the proper number that will give you the non-trivial solution. So these are eigenvalues. And then for the eigenvalues, for each n, we're going to have the corresponding eigenfunction, or the eigenfunction that associated to eigenvalue. So right here, so the eigenfunction, see this form. We're going to ignore the C, as you recall, just the fundamental problem or fundamental function. So yn equals psi of omega. Omega is 4n, right? Omega is 4n. So it's going to be psi 4n times x. So we have pieces that the problem asks for. So eigenvalues, the lambda n is 16n squared. Eigenfunction associated to eigenvalue are yn equals psi 4nx. So for n equals 1, for this equation, we're going to get the solution y1 as psi of 4 times 1 times x, going to be psi 4x as a solution. For the second one, we get the corresponding eigenfunction as y2 equals psi 4 times 2 times x, which is 8x. So that means you can choose the option of the lambda to obtain the non-trivial solution. And for the spring problem, so if you recall, this is m y double prime plus k times y equals 0 in 5.1. So that means you have y double prime plus k over m times y equals 0. K over m here is omega squared.